Okay, so I'll just introduce once again. This is Colin, he's a product manager from NATS. And Wally, also one of the core contributors to the project. And I have been using NATS-based systems for a while. It seems like around 6 years already. So it's really cool how NATS is really taking off now, joining the CNCF and the growing ecosystem. So really thank you for attending. And this is going to be an extension from the previous talk. If you have any questions during the talk, just raise your hand and it can be interactive and solve as many questions as we have, as this is the last talk. And so this is a deep dive into the NATS project. Okay. So for this, I have some slides and agenda for this session. I want to show you some of the design from both NATS and NATS streaming. Some of the how they work and how those NATS streaming fits into the picture. Give some highlights from the NATS ecosystem, and also I give you some demos of usage examples of how to use NATS. So let's start with NATS. And I already mentioned by Colin earlier, but it's a high-performance messaging server within Go. It was originally written in Ruby in Event Machine. This was in 2011 for Cloud Foundry. So NATS was like, the message bus used for the command control, doing the command and control between the components in Cloud Foundry. And in terms of performance, it was still pretty fast, had around 150,000 messages per second. So it worked very well, like for even those, in spite of those limitations. And the foundations are still very solid since then. I mean, like the protocol is pretty much the same still. It is the implementation is again, it's a pure poly-subscribe system on top of TCP/IP. You can use secure connections with TLS. And from the rewrite, the binary name is GNATS-T. We have thought about changing into the NATS server, but at this point, GNATS-T has stuck. And this is a simple example of the protocol. We have an example demo endpoint. You can use telnet into it. It's telnet demo.nats.io in the port 4222. And as you start establish a connection to the server, the first thing you will get is this info string with some metadata of how to handle the connection. And one of the important fields here is the maximum payload size. So all the messages that you send to NATS are constrained to 1 megabyte by default. You can tune this in the server if you want to send like larger messages. And these are some of the basic publish subscribe features from the server, right? So here we are making a subscription into the hello.copenhagen subject and publishing on this subject 5 bytes. This is going to be just the world message. And since this client has registered interest into this hello.copenhagen subject, then the server is going to announce it that you have one message on this hello.copenhagen that's matching the first subscription that you made, and it's 5 bytes in total, right? So the server is telling you how many bytes you are should be reading from the server, right? So this is what allows you to the server to be payload agnostic, right? So and you don't NATS doesn't constrain you to any type of encoding serialization format, right? You can use protocol buffers, JSON, message pack, whatever fits your needs. And the complete protocol is just these 10 commands. You can publish, subscribe messages. There is an unsubscribe command where you can define a priori how many messages you want to receive. For example, you can say, I only want to receive 5 messages on this subscription. After that, just fade away and stop receiving them. And you can customize your connection against the server using connect. And this is important when handling credentials, for example. There's the info protocol, which is used both by sharing metadata to the clients and also for gossiping the network to topology from the cluster, right? So this is the way the auto-discovery mechanism it works, right? So as soon as a new server joins the cluster, these network locations are gossip to the clients. And also, well, yeah, messages, the message protocol, which is for processing the messages, and there's errors that notification that the server can send. This plus OK is for when you have the verbose mode from the server, which is activated by, disabled by default for the clients, right? And there's ping and pong always happening between the clients and the server. So periodically, every 2 minutes, there's going to be a keep alive happening so that the connection is always healthy. This is a simple example of using the Go client. The Go client is the one that is get the most, well, it's a canonical implementation for what NATS client, well, with the behaviors from NATS client. And here we have an example of an asynchronous subscriber subscribing to this hello subject. It takes a callback. It has a very similar API for all the other client implementations that we have. And as soon as we publish a message on the hello subject, then this, well, it would print that you received this message, right? And the server, it's again, it's a 7 megabytes binary, no dependencies at all. You have you can grab one of the latest releases in GitHub and / releases. This is the latest version right now, version 1.1.1, and I can start sharing some of the examples of how things works with NATS. Some basic usage of the NATS server. So can everyone see? It's too small. Yeah. Okay. So this is the starting GNATS is fairly straightforward. It has by default is going to be listening on the port 4222. There is an extra port that you can open for gathering metrics from the server. This is the port for 8222, and as just smoke test the connection. Yeah, some simple subscriptions. Hello, Copenhagen. Yeah, the protocol command. Hello world. Okay, so we can do the same with the clients. I have some examples here. So you have multiple well, messaging patterns, right? So you can broadcast one-to-N communication by using a pure polysubscribe. There's also a request response that will guarantee like doing the one-to-one communication. And also there's the queue subscription that you can use to for doing the load balancing, right? So simple example is just doing a request reply. Well, just a periodic timer. This is so yeah, this is a simple client just connects to NATS and it's going to periodically sending a message every second, right? So let's start it. This is not here. Keep on. Let's publish. Go. Can't find go. Okay, so now we have periodically sending messages. And let's add another subscriber. Let me see, where am I? Here. QCon. Now I'm going to add a client that is going to subscribe into the hello subject and start receiving these messages. So yeah, it started receiving all of these messages. And something that is, so there is a support for wildcards in NATS, right? So if you are interested into auditing all the traffic that is happening right now, you can use, for example, the full wildcard that will make this new client receive, basically tap into all of the traffic that is happening right now. So, and this original subscriber will still be able to consume all of those messages. Then let's see what happens if I kill the server. You will see that the client in the middle continues to publish messages, even though it is still not connected, right? The reason for this is that the client has an internal reconnection logic happening. So every 2 seconds, it's going to try to reconnect to the server. And it has like 8 megabytes buffer where it will continue to accumulate pending data until it's able to reconnect. So once we reconnect, it basically make a burst of all of the messages that were accumulated during the downtime from the server. And this is for the one-to-one communication. And because I exposed the monitoring endpoint, so I can use a NAT stop to monitor all the connected clients. So let's increase the number of clients. Say. Okay, so now we have 20 clients that are consuming all of these messages. And this will get very chatty very, very fast. So there is another API that you can use, which is the QSubscribe. In this case, we can modify this subscriber to use a Q subscription and name a group for this set of workers, so that instead of everyone receiving the message, what happens is that the server will randomly balance these to just only one of them. So if we run once again, now you can see that randomly the server will be sending the message to only one of them. And the third important feature from the server is the request response. So you can do so in this case, I'm going to be sending as many messages as I can on the hello subject, and giving up after 200 milliseconds. So let's okay, requester. Yeah, there was a timeout, so. I'm going to use a queue group. Subscriber. Okay. There is what's up? it's connected. So by passing the -d, -v flags into the server, you can enable verbose login for the server, but this hits performance a little bit. So it's very useful for a production-ready setup. Yeah, it's can increase the latency from the request. So in this case, yeah, there's no errors and it's able to communicate. It is getting 100 microseconds response times, but it would be faster if I remove the verbose. Yeah. Yeah, so these are like the three main features that you can get from NATS. One-to-one communication, publish subscribe, using the load balancing groups with queue subscriptions, and request response for one-to-one. And the rest of the features from NATS, the NATS project just built on top of these main three building blocks. So back to the presentation.
While Wally's going back to the presentation, one of the things you can do is combine the load balancing with request reply. So you might have several repliers out there ready to reply, but then send a request and it'll go to any one of the 7. It's a great way to load balance and scale. So if you find you're taking too much time processing your requests, you simply scale up more. If they're in the same queue group, only one's going to respond. So you can scale up 30 or 40 if you have to as load increases, and then scale back down again.
Yeah, thank you. So moving on to some of the operational aspects from NATS. This is what a usual production setup for NATS would look like. You would have a set of NATS clusters so that you have high availability. There are 3 main ports they would be opening. This 4222 for the clients to connect. There is a 6222 for the clustering peers to connect to each other. And then for monitoring purposes, in case you want to just poll yourself via some tooling like NatStop or Prometheus Exporter. For the high availability, you need to set up the NATS clusters to be in a full mesh, one hop setup. And as a client, a NATS client doesn't really need to, only requires to be connected to one of the, to any node as part of the cluster, right? So it doesn't, then the NATS cluster will be responsible of routing the messages according to the interest graph, right? So in this case, if this client publishes a message to this server, I mean, all of the clients that are connected to this same server are going to receive the message, and also the ones that are remotely interested into this message are going to be receiving them. Setting up the NATS cluster can be done by just using the auto discovery mechanisms. So in this case, the first one, note that it doesn't have this -- routes parameter. So that one is going to become the seed server. Then the second one will join, and it knows that there is at least one seed server at this 6222 location. And then the third node is going to be joining, and then the full mesh NATS cluster will be assembled. So in terms of the protocol, how it works internally is that it is leveraging the info command to gossip around what are the URLs that are available inside of the cluster. So once this joins, then the other node is going to connect to this other one, and that's how the full mesh setup is is assembled. And then all of the clients that were connected to these other servers are going to receive also the network location. So now they will be they will add this end into their own into the pool of servers that they can reconnect. So in case this server now fails, the client will fall back into the reconnection logic and then transparently reconnect into this other server that just joined. So it automatically fails over. There's a capability to set up secure by default the connections. So you set up the server to use certificates. Then any client that wants to connect to the server has to establish TLS, right? Here, once again, the info command is used. When you set up the TLS in the server, then it's going to announce you that you should start the TLS handshake. Otherwise, you will not be able to continue communication. Then the TLS handshake happens, and then you can continue communicate as if we're as usual. Complete secure NAT setup would involve both securing the port for the TLS for the clients, and also you can use a different set of certificates for the clustering peers. So, and also you can expose the HTTP endpoint to use HTTPS to be able to securely scrape the metrics. And this is one of the most important features from NATS, which is how resilient it is. And Colin mentioned it earlier in the intro. There is a concept of slow consumers that NATS really optimizes for this use case where, let's say that, for example, there is a client that is subscribing to us into a hello subject, but it is not being able to process all of these messages that it is receiving, right? So if the server starts accumulating too many of these messages, it is going to give it 2 seconds deadline to drain everything that is being sent to the client. And if it doesn't read all of those bytes, then it will disconnect the client and tell it that it's a slow consumer. When you get to this point, it is already kind of too late. So as part of the application, what you ought to do is, for example, in case of the asynchronous subscribers, you could cap the length of how many messages should be pending. For example, by default, it's 65,000 messages, but you can lower those so that you can detect earlier that there is a slow consumer error at the application layer, at the application level. So, and NATS, and then next I want to cover NATS streaming. And NATS streaming builds on top of all the previous pieces. It is request response protocol using the request response API from NATS. And because NATS is a protocol payload agnostic, we need to decide to use some serialization format. We decided to use protocol buffers in this case. And the code name is Stan because we say that it's the complete opposite from NATS. So while NATS gives you the at most once delivery guarantees, and it really optimizes for keeping things simple, and there is a little bit more state as part of Stan and the NATS streaming server. So you have a persistence of messages, you have the storage, then there's all this hacking happening between the clients, and so to ensure that they're consuming the message. So just in the client libraries, you would see this name Stan, like import Stan, which is much shorter than NATS streaming. It is essentially a NATS application. So what it reuses for an already available NATS cluster, for example, and it connects to NATS and uses it as a transport to enhance the delivery mode for NATS. So in case we have NATS streaming client libraries for different application runtimes, so they implement the request response protocol from NATS streaming. And it allows you to make a publish and then ensure that it is persistent, and then it is act. And the ones that are subscribed will be able to replay from the beginning all the messages or just for a certain point. And you can reuse this same cluster both for using NATS streaming or just regular NATS applications. And because it is built on top of NATS, you get all the same set of features for the reconnection logic and high availability clustering. So in case one of the NATS servers goes away, then we'll reconnect to another one of the available NATS servers. For now that you have a state, then it's the high availability for NAT streaming itself comes also into the picture. So one of the ways to solve this is by the fault tolerance mode from NAT streaming. So in this mode, you can have a single NAT streaming server become the active server that is going to be persisting the messages on well, the active server. And you can have a set of standby NAT streaming servers that will become active in case the other one fails. And there's also NAT streaming clustering support by using Raft. So the way this works is by, with following the Raft consensus algorithm. One of them becomes the leader, and you can have a set of followers that are going to be replicated all of the logs of the messages that are published to NATS. And since you are reusing, you can have a multiple set of NAT streaming servers using with different names, right? So you can have let's say a cluster A NAT streaming server alongside cluster B, and they're all reusing the same NATS cluster. And but by default, if you try NAT streaming, actually what happens is that NAT streaming is embedding the NAT server. So you will run NAT streaming with an embedded NATS server where that is connecting to, and then you can also deploy this way where without having to, in case you don't have another available NATS cluster. So moving forward some of the pieces from NATS ecosystem, we have available Docker images for both NATS and NATS streaming. They are very lightweight. We're using the from scratch approach so that they have very few layers. The NATS streaming, the NATS one is like 7 megabytes. It's one of the first official images that was using this approach from scratch. We have a Prometheus exporter, and we showed at the keynote where you can configure it to scrape the metrics from a server exposing the monitoring endpoint. And another very cool project is Glue. This is very sophisticated. What it does is they actually implemented their own C++ clients for NATS and NAT streaming as part of Envoy. And here's a link for the demo. It's basically it's like this event gateway where you can make HTTP requests and then publish these messages through NATS. And so you're gonna use some people are familiar with the flow that you get from gRPC, and there's an interesting project in the community named NRPC, which is gets you to some middle ground here where you can use protocol buffers on top of NATS. So then you can take advantage of some of the load balancing features that you get from NATS and doing the pop subbing. And also there's the operator that was originally developed by Paulo Pires, and that so this is you're using a Kubernetes, a simpler way to deploy NATS clusters where configuring the full mesh in a very simple way. And this is an example manifest from NATS operator. So far, any questions? I mean, yes.
I'm curious about authentication and authorization.
Yeah.
Do you have any pluggable abilities for like authorization policies so that I can, once I've authenticated a client, I can dynamically program what they're allowed to do and what they're not allowed to publish to or subscribe to?
You want to take it?
Sure.
So the question was about pluggable authentication and authorization. It's been a long few days. Right now, today, we don't have anything pluggable, but what we allow you to do is to rewrite the configuration file and then send a signal to the NAT server that'll then reread and apply all the differences. So if you want to, let's say, remove a user or revoke their creds, then you can just simply remove them from the configuration file, send a signal, it'll reload and actually kill all the connections that that user is associated with. Sometime in the future, we aren't exactly sure when, we have plans for a pluggable interface. That may happen sooner rather than later, or later rather than sooner, I mean, but we'll see. But some sort of pluggable interface that'll let you call out to whatever you need to, OAuth or LDAP, whatever.
So if I wrote an operator to do that kind of stuff on top of NATS, that could work. And the same goes for authorization. It wouldn't kick everybody off like every time I reloaded the policy.
The question was, would authorization changes kick everyone off? No, it would only kick off the people that were the user, the connection ID that was affected. And it's the same with permissions. So let's say you had somebody, you had Colin publishing to foo, and then you change the permissions where Colin could no longer publish to foo. That would just stop.
Yeah, so
How big clusters have you tested with? Have you tried to maximize the limit, or what is the performance impact of going into a cluster with NATS?
So the question is, how big of clusters have we tested with? I believe there's been some users that have had clusters in the range of 50 to 100 servers. And it's kind of a tricky question to answer as far as the penalty. It depends on how many subscriptions you're making, at what rate you're making of subscriptions. So if you're making hundreds of new subscriptions a second, that interest is propagated throughout the cluster. You'll have a penalty. If you have a fairly stable number of, or static number of subscriptions, where maybe just a couple a minute, then you can scale actually quite a bit further because you don't have that interest propagated. You don't have that chatter between the servers. Yes?
Do you support also exactly once, if I know that pattern, or is it in your roadmap or something?
The question was, do we support exactly once? The answer is no. I don't really think we'll ever support exactly once. There's a few reasons for that. With newer applications, they tend to be designed to be idempotent. And when you implement exactly once, there's a lot of mechanics behind the scenes that really incur some big penalties. The other thing is that exactly once doesn't actually protect your application's processing. So let's say you've received your message, you start to process it, and you crash halfway through. Well, you're either going to have to roll or crash halfway through, right? If you did any sort of storage into a database or anything like that, you're going to have to do some cleanup or fixing later on, in which case most people just use the idempotent approach. Let's say you detect an error, then you're going to have to roll back and then not act that message and re-receive it anyhow. So exactly once, there's just very few situations where people really need it. I get the sense a lot of users think they need it when they don't, and in fact end up having to make things idempotent anyhow to make their system stable. That's my opinion. I could be wrong, but long answer to no and probably not. There's someone in the back that's been.
Regarding your staying with that topic with the at least one solution using the student server, how do I scale that solution? Like, how do I make it highly available? Maybe I just missed it, but your NATS cluster is like one logical messaging cluster. When I use the streaming server, I have like individual separate apps. Of course, I can deploy multiple ones, but they're not one logical cluster anymore. So how do I like scale horizontally and make it highly available?
Okay, the question was, with streaming servers, how do I scale horizontally or make it highly available? Is that? Yep. So what we can do with streaming servers is, for high availability, you've got two options. You can use Raft, which is your clustering. We also have a warm failover mode, where you might have a few instances running that aren't actually doing anything, but they're ready to pick up as soon as a primary instance fails. And that's your high availability option. As far as scaling, we allow you to partition servers by subject. So you might have a streaming server that handles subjects foo and bar, and another streaming server in the same cluster that handles BAS. And that's how you scale. So you scale horizontally by subject rather than like in other messaging solutions by partitioning. Lots of questions. Sure.
Yeah, so like in the streaming use case, where do you guys buffer the data? So for example, do you guys do replication for the buffered data, like for the unactive data? Also, like you mentioned, when the leader fails, are those data like still retriable?
So the question was about buffering data and streaming, and when do we act? How do we manage that? So there's two modes in streaming. So we support an F-sync mode, which means the servers do not respond to the raft log append with an OK until the message in question has been F-synced to disk. We also offer a mode that allows that message to be buffered onto the disk for better performance and for people that are okay, because you're going to have a quorum, so you're going to have maybe 5 instances. So that's one part of that. And then it's just the nature of the raft protocol. So a client will send a message to a NAT streaming server, and before the NAT streaming server acts back saying, I'm okay with that message, it makes sure that at least a quorum, at least 3 of your 5 servers have successfully persisted that message. Yeah.
If I have multiple Kubernetes clusters, and I want like a global messaging fabric that's able to go across the clusters with say NATS, I'm going to guess you wouldn't recommend that I take all the NAT servers and fully mesh them across my clusters around the globe with cloud providers. You probably want independent ones, right? What pattern would you recommend then for me to still have a somewhat global federated messaging bus?
The question was, if I have multiple Kubernetes clusters and I've got NATS deployments in each one, but I want to connect all of them globally, what pattern would I use? Today, you would still need to do the full mesh with what we have today. We actually are working on bridging different clusters together to solve that exact problem. And we should have that definitely by Q3. Way in the back, by the door.
What's the impact on performance if you use huge messages, like 1 megabyte?
There is an impact on performance. I mean, you have quite a bit more memory copy from your socket into memory and then back into every other socket. So it depends on a couple things. Since it's a memory copy, it's going to depend on some of your CPU. It's going to depend on how big your pipe is, what sort of network you're working on. So the answer is, yeah, there is a performance impact. How much depends on your resources at hand. We default to a meg, but you can go unlimited. Yes.
Is there something like application-specific headers, or do I have to put everything into the payload? For example, when I have microservices, I usually want to pass along a correlation ID for logging, so I know which log entry belongs to which request.
So the question was, are there headers in NATS so I can pass things like a correlation ID for a message? The answer is no. We've intentionally chosen not to include headers in NATS, and that is part of the payload. So NATS is entirely payload agnostic, and to that end, even with headers, we don't include anything. But they can certainly be added on, and that's exactly what we did that Wally mentioned in NAT streaming with using protobuf, because we needed headers. So we just used protobuf for that.
Yeah, so here you can see some of the examples of running a NAT streaming, and it is using just the NATS protocol, and because it is payload agnostic, then everything is published as protocol buffers, right, for NAT streaming. But So yeah, you have to do it. Choose one and then do it on your own.
So we have just a few minutes left, so a few more questions.
Is there any tracing capability built in using the open tracing, some kind of having everything on that?
Yeah, the question was, is there any tracing facility built into NATS? No, we actually have to push that up to the application because we don't have headers. So the application will want to have some sort of correlation ID or unique ID for tracing, like open tracing with Jaeger or Zipkin or something like that. So yeah, the answer is unfortunately the application has to do that. You haven't asked a question yet, right?
Yeah.
Okay, go for it.
The question, what is happening if you have problems with latency? Will all the clients be cut off because of the 2 seconds limit?
If all your clients have that much latency, then yes, they will. The server will continue to buffer up, and then your clients will be cut off. But in that situation, if you're dealing with an extremely high situation, a latency situation, you just increase that to 10 seconds.
Even if it's minutes?
Even if it's minutes, you can do it. It depends on your environment. If you have latency of minutes, for a single message to get through, I suggest you look at other areas first.
Share some numbers on like the large NATS cluster you've seen and on the numbers on highest throughput you've seen.
Okay, so we've asked for numbers on the largest cluster we've ever seen and throughput. So largest cluster, it was between, I think, close to 100 nodes in the cluster. As far as throughput goes, some of our recent tests with multiple streams, Derek got 80 million messages a second, aggregate. One just single pass through, one publisher, one subscriber. I think we're about 21 million messages a second.
Yeah, so here in the background is okay.
We'll let Wally show, and then
Yeah,
and then I think we have to call it.
yeah, just an example of having a tight loop and processing, not being able to process all the messages that are being sent, and then client is trying to reconnect, and then just the server continues to say that slow consumer detected and chopping the connection.
Okay, well, I'll let Wally close. This was his demo.
Well, thank you for attending,
Yeah.
and we'll still be here until keep going. Yeah. So.
Yep. So if you feel free, come by, talk to
Yeah.
us. We're jet lagged, but still.
Yeah, we have maintenance hours as well tomorrow. I think tomorrow morning. Mm-hmm. Yeah. Well, thank you.
Thank you very much.